All right, folks, let's go ahead and let's get started with the material today. I hope yesterday's video was a little bit shorter. You were able to get through. A few of you actually needed extra time, so I'm glad to see that. But again, try to get as much done as you can. Try to finish it um, uh, within the period, but if not, just let me know, email me or comment in Google Classroom and let me know. And then that ways I can just respond and give you more time. Okay. I'm going to, again, try to aim for about 25 minutes of lecture time here, or video time. I'll go ahead and time it. And then that'll give you some time then, give you an opportunity to make sure then that you are able to get the work done in the video and the couple problems that I'll ask you to do at the end. Okay, so I'm going to go ahead and I'm going to make sure then that I keep my time on that I'm on track. So I'll go ahead and get started with that. Okay, I'll start the timer. And so we'll start then with a quick review. Just remember yesterday I introduced you to the mole ratio. The mole ratio, basically, we obtained that from the balanced equation. And the mole ratio basically just compares the parts of the reaction. Compare the moles of the reactants to the products, reactants to each other, or products to each other. So basically, it is a ratio that we use to compare the different parts of a chemical equation. Okay. And so what I'd like you to do here, so we'll start out fairly soon. What I'd like you to do here is go ahead and on your paper, go ahead and make sure you balance the equation first, balance the equation, and then derive all the possible mole ratios that can be obtained from this particular equation here. Okay, so take about a minute or two, write down as many as you think you have, and I'll go over it with you, and then make sure you write down your answer and then compare your answers to what I have here for you. Okay. All right. So it can take about a minute or so to get that done. Okay. So let's go ahead and let's take a look at the equation here. Hopefully you recognize that the equation here is not balanced. Okay. So you got to make sure you balance the equation. I'll leave it up to you to try to make sure you balance that. But in order to balance this equation, then I will write down the. Remember, this is a combustion reaction. So balance the carbons first. Then the hydrogens and the oxygens, you'll notice here then that the very first reactant, that has an oxygen in it. So it's going to make balancing a little bit more challenging, but I think hopefully you got it. But the balance equation then, if you get this done, it's going to be 2,9. So we'll write this down, 2,968. So 2,968 are the coefficients that'll balance this out for us. Okay. With that said, then let's go ahead and write down the mole ratios. Essentially, what you'll do is just pick two and then write the ratio for it. So, for example, the first mole ratio I'll use to compare the two reactants. So then we'll have 2 moles of C3H7OH, which is propanol, over 9 moles of oxygen. And there it is. There's 1 mole ratio. Remember, this is a conversion factor. So in just a moment, we're going to see how we can use this as a conversion factor. But as a conversion factor, what we need to make sure we recognize then is that what we're saying is that these 2 moles of propanol is exactly equal to the 9 moles of oxygen. Meaning then, to run this reaction, we need exactly 2 moles of the propanol to react with 9 moles of oxygen. So this is an equality that we can take advantage of. Why? Because if we use this as a conversion factor, this ratio then is going to be equal to 1. So when we do the conversion, we're essentially just multiplying by 1. Okay, so make sure you keep in mind that what this mole ratio means is this equality right here. Okay. All right, so let's go ahead and let's find the other mole ratio. So we've compared propanol to oxygen. Let's just take this and then compare it to carbon dioxide. So to make the second mole ratio, then we'll set it up as 2 moles of C3H7OH. Okay, so 6 moles of CO2. Okay, all right, and then finally we'll make a mole ratio out of C3H7OH here in water. Okay, so let's go ahead and write that down. So we have 2 moles of C3H7 OH over 8 moles of water. Okay. All right, so there it is. We partnered propanol up with each one of the other components of the reaction. So let's go ahead then and let's do the same thing with oxygen. So oxygen, we've already formed a ratio with propanol here. So let's write down the mole ratio between oxygen and carbon dioxide. So that'll be 6 moles of CO2. Okay, and then we can form one last one between oxygen and water, and so we have then 9 moles of oxygen and 8 moles of water. Right. So we have oxygen now paired up with each one of these. And so you can see then the last mole ratio, then the mole ratio then will compare, and the mole ratio will be the ratio between carbon dioxide and water. So let's go ahead and write that down. We have 6 moles carbon dioxide over 8 moles of water. Okay, so we have then 6 unique mole ratios that we can form from this balanced equation here. Okay. Now, what we do with these mole ratios then is we can use them as a conversion factor. So when we do the conversion, if this is the reaction that we have to convert for, then you would pick the appropriate mole ratio, pick the appropriate conversion factor in order to get the conversion done. Okay. All right, very good. So coming up with the mole ratio is important. You got to be able to identify the mole ratios. What you have to be able to do is, again, like I said, we're going to use these as conversion factors. And so let's take a look at a problem here where you're going to be asked to do that. Okay, so let's go ahead and read this problem here. Okay. And so you have you want to write the mole ratios, and this is going to be the mole ratios from the reaction of what we call the Haber process, which is going to be the reaction. I'll write it down here for you again. The reaction between nitrogen and hydrogen gas to produce for us ammonia gas. Okay. And so when we came up with that balance equation, let's go ahead and balance this really quickly. It's going to be 2 here. That will give us the balance equation. We got 6 here. H2 here, sorry. This is H2, sorry. And 3 here. And that'll balance out the equation. Okay. All right, so real quick then, just to use this as a review, the mole ratios that we can come up with here then is going to be from the balance equation. It's 1 mole of nitrogen for every 3 moles of hydrogen. That's 1. Second one then is 1 mole of nitrogen for every 2 moles of ammonia. All right, and the last one then is going to be 3 moles of hydrogen. So we'll take this and pair it up with 2 moles of ammonia. Right? So 3 possible conversion factors to choose from. Let's take a look at what the problem's asking us to do. Okay, so remember, if this is a conversion, we want to identify what we start out with, what we want to solve for, and then pick the appropriate conversion factor. Okay, so hopefully everyone sees here then that we are given 6 moles of nitrogen. Okay, so we're told then that we have 6.6 moles of nitrogen reacting with a certain amount of hydrogen. What they're asking you then is to find the moles of ammonia. So how many moles of ammonia are we going to form, okay, if we start out with the 0.6 moles of nitrogen? So let's go ahead and let's write that down. So what are we starting out with? Our conversion, we're starting out with 0.6 moles of nitrogen, okay? And we want to solve for the equivalent amount of ammonia, so moles of ammonia that will be produced. And so if you take a look at this, which one of these 3 conversion factors? So we've come up with 3 conversion factors here. We're obviously not going to use all 3 of them. We're only going to use the one that allows us to do this conversion between nitrogen and ammonia, the moles of nitrogen and moles of ammonia. So we'll go to one of these 3 here and pick the one that has moles of nitrogen and moles of ammonia in it. We see that the middle one right here. Okay. And so we're going to plug that in. Now we may not plug it in as written here as 1/2. Remember, we want to cancel out this unit first. Cancel out this unit. So we'll plug this in. So that'll be so we cancel this unit out and then for this one. So if you take a look at this, just ask yourself, if we leave it this way here, moles of nitrogen would be on top, moles of ammonia would be on the bottom. And so the unit here of moles of nitrogen will not cancel out. However, if we flip it around, if we flip it around, we put 2 moles of ammonia on top, and we place 1 mole of nitrogen on the bottom, okay, which here then you see then that you will get those to cancel out. You end up with moles of ammonia on both sides, and then you go ahead and just plug that in your calculator, and you end up with 1.2 moles of ammonia. And so the conversion, these conversions are requiring the use of the mole ratio are very straightforward, very easy conversions for us to do. Okay. All right. So what I would like you to do then is go ahead. Let's take a look at number 17 in your problem set here. Read the problem carefully. What I would suggest you do is write out all the mole ratios that you can obtain from this balance equation. For now, I would suggest that you do that, and then pick the correct one that you'll need to do the conversion. And since this is a conversion, make sure you remember, ask yourself the 3 questions. What do you start out with? What do they want you to solve for? And which one of the conversion factors will you need to get that done? Okay, so take about a minute or 2 to get as much done as you can. And then when you get back, I will go over this problem with you. Okay, so go ahead and get started with this. All right, then. Let's go ahead and let's take a look at this problem here. Okay, this problem then, we have this equation. If you take a look at it, it's a balanced equation already. Okay, and so let's go ahead and let's ask 3 questions. Okay, so if you take a look at what they gave you in the previous problem, hopefully you recognize then that what we're starting out with is going to be 3.7 moles of aluminum oxide. Okay, but what I'd suggest that you do before you do that is go ahead and write down the mole ratio that you can obtain from this balanced equation. So let's go ahead and practice that. Okay, so we have then 4 moles. You will have then 4 moles of aluminum, and we'll make the ratio between aluminum and oxygen. We have then 3 moles of oxygen. That's 1 mole ratio. Okay, aluminum to aluminum oxide then it'll be 4 moles of aluminum. I'm sorry, moles. Erase that real quick, sorry. Okay, so it'll be 4 moles of aluminum. 4 moles of aluminum, and that will be to 2 moles of aluminum oxide. And the last mole ratio that we can obtain then will be oxygen to aluminum oxide, which is going to be 3 moles of oxygen to 2 moles of aluminum oxide. Right? And so those are the 3 that we're going to choose from. We're only going to use one of them, though. So let's go ahead and figure out which one. To figure that out, let's go ahead. We were told from the problem then that we start out with 3.7 moles of aluminum oxide. So we're given that. Okay, so again, from the problem itself. Okay. And what they're asking me to solve for then here is the moles of aluminum. So they're asking me to find then how many moles of aluminum will you need. Essentially, that's what they're asking you to do in order to form this many moles of aluminum oxide. Okay, so let's take a look at our the 3 options here. We need to find the mole ratio that has the aluminum oxide and aluminum in it. And so if you take a look at that, it looks like the middle one again. This one has both of them. So we'll use that one in order to do the conversion. Okay. So finally, do we plug it in as 4/2 or 2/4? Well, we want to plug it in such a way where moles of aluminum oxide here cancels out. So if we plug it in as 4/2, take a look at that here. If you plug it in as 4/2, then the aluminum oxide, moles of aluminum oxide will cancel out here. And we're left with moles of aluminum on both sides of the arrow. And so our conversion so far is correct. Okay, so let's go ahead and plug in our numbers. And then we end up with an answer here that is 7.4 moles. Okay. Folks, be mindful of significant figures here. There's 2 sig figs here, and with the starting amount, we'll need 2 sig figs here as well. Okay, so make sure you are mindful of significant figures when you get this done. Okay. All right. Well, I hope I think that's pretty straightforward, folks. I don't think that's going to be an issue for many of you. I think practice writing down the mole ratios, practice doing these problems on tonight's homework. And like I said, if you're having issues with this, come on by after school today, 3:15 to 4:15 on our Zoom Meet site, and then ask your questions. It'll be live. You can ask your questions, and I'll work them out for you. Okay? But remember, um, moles, we can't measure out moles. There aren't ways that we can measure out moles. So this is useful for us to do this conversion, but it's not practical because we can't carry out the reaction. We can't measure out the moles of aluminum here, for example, or moles of aluminum oxide and predict that. And so what we have to do is we have to have a way that we can convert these mole amounts, these mole quantities, into either mass quantities or volume quantities. And hopefully you remember from back in chapter 10, we do have a means to do that. We can either use the molar mass to do the conversions from moles to mass, or we can use the molar volume if we want to convert from moles to volume, okay, with the conditions of STP and that the substances have to be a gas. Okay? All right. So for example here, let's say then that we had 100 grams. So we start out not with 3.7 grams, but we were told that we have 100 grams of aluminum. We start out this reaction, we start out with 100 grams of aluminum, okay? And we want to find out then, if we start out with that much aluminum, how many grams of aluminum oxide would we form? That's the conversion that we want to be able to do. We want to be able to go from the mass here of aluminum and to predict then how much aluminum oxide that we will get if we start out with 100 grams. Folks, the answer to that and the method that we're going to use to solve for this one is what we call stoichiometry. This is the stoichiometry, and this is the title of this chapter. The stoichiometry then is the math that we do, the conversion we do to find amounts. Okay? And so this is very important for chemists because we need to be able to carry out our reactions without wasting too much of these reactants, and also being able to predict how much product we're going to get, so we can go ahead and do percent yield calculations to determine then how well the reaction ran, how well we did our work. Okay? And so my hope was, unfortunately, we won't be able to meet to do the lab, but the lab that you were going to do was going to give you a chance to practice this calculation. And the prediction here of the amounts here is a very, very useful tool for us to use, is that we can make all sorts of assessments about how the reaction ran. Okay. All right. So what we are essentially going to be doing then is we're going to be doing this mass-to-mass calculation. Okay. And in doing so, then understand the central conversion factor that we're going to use then is the molar mass. And then after that, we'll use the mole ratio. So those are the two basic conversion factors that we'll need to get this done. Okay. So what you need to make sure you understand then is with the molar mass and the mole ratio, the molar mass you have to calculate for, and the mole ratio is you can get directly from the periodic table. Okay. All right. So let's go ahead and let's trace what we'll be doing here. Okay. So the idea here then is we want to start out with, or we are given a mass, or we start out with the mass of a reactant or product even, okay? And we want to find out then the equivalent mass of another component, of another substance in the reaction itself. Understand this, we can't do that directly. There is no mass to mass conversion that we can do. There are no conversion factors that allows us to do that. We haven't learned about it yet. However, we do know this. If we have the moles of this first product, and we have the moles of the second one, we just learned how we can do that conversion by using the mole ratio. Okay, so we can do that using the mole ratio. So again, there are no conversion factors here that allows us to convert from mass of one compound to the mass of another compound. That cannot be done. But we do, and we just learned it, we do have a means to convert between moles of one compound to moles of another compound if we have the balanced equation using this mole ratio. However, this is the goal that we want. We're going to be able to find out what the relationship is here. So with that said then, we need to go through here. So my question then is there a way that we can convert between the mass of of this first substance and the moles? And absolutely, we learned that back in chapter 10. We used the molar mass. So here we would multiply by the molar mass in order to get, divide by the molar mass in order to get to the moles of the compound here. Once we are here, we can use the mole ratio to get the moles of the second substance here. Now, the issue then is we don't want the moles, if the problem is asking you to find the mass, is there a way that we can go ahead and get from the moles of the second compound to the mass of the second. And the answer there then is absolutely yes again. We use the mole mass of the second substance. Okay? And so what I've done here is I've shown you a flow chart that we would use in order to get from mass to mass. So we can't do it directly. We can't do that conversion directly. That is off limits to us, but we can do it indirectly in this manner here. Okay, so you want to keep that in mind as we go through this. Okay, so that's what we're going to do. Okay, so let's go ahead and let's take a look at a problem that's going to help us practice that. Okay. Okay, using the familiar Haber process again. Okay, so let's go ahead and write down the balanced equation for this. Okay, the balanced equation for this then is going to be, and we always want to start out with the balanced equation. Okay, always with stoichiometry, always start out the balanced equation. We have 1 nitrogen, 3 hydrogens, okay, to give us 2 ammonia. So that is going to be the balanced equation for the Haber process. Okay. So let's go through now and let's see what we are asked to do, okay, and what we're given to get that done. Okay. So we were told then that we have 5.4 grams of hydrogen. Okay. Now, we were given the amount of hydrogen here, and I'm going to write that underneath here just so we can remember. And this is a technique that I would advise that you do. Okay. So we were given that amount of hydrogen. Okay. And so we were told that we have excess nitrogen. What that means is that means we have more than enough nitrogen to run this reaction. We don't have worry about the amounts here. And so they're asking us to find then the grams of ammonia. Okay, so this is what we're starting out with. This is what we're solving for. So we are solving for that right there. Okay. All right. So until you get comfortable with it, what I would suggest you do is write down the mole ratios again. Make sure you are aware of the mole ratios that are available to you. I'll just write that down here really quickly. We have then 1 mole of nitrogen, okay, for every 3 moles of hydrogen. Okay. We have 3 moles of hydrogen for every 2 moles of ammonia. And then finally, 1 mole of nitrogen for every 2 moles of ammonia. Okay, so those are the conversion factors. Let's go ahead then and let's write down the problem. Okay, so we are starting out with then 5.40 grams of hydrogen. We were told then that we have this amount of hydrogen to start out with, and if we have more than enough nitrogen in order to get this reaction done, they're asking us then how many grams of ammonia do we need, will we produce? Okay, so that's the final. All right, so let's look at what we have here right now with our conversion factors. With these 3 here, do we have what we need to solve this problem? Well, no. Here we start out with grams, and here we end up with, there are no gram units here at all. And so we need to introduce that in somehow. So we have our set of conversion factors here. We have one set that we can use, but obviously I hope you can see then that we need more. Okay. First of all, we need to be able to convert the grams, the mass of the, remember in the previous slide with our flow chart, we need to be able to convert the mass of hydrogen here into moles. And so therefore we need the molar mass of hydrogen. It's going to be 1 mole of hydrogen for every 2 grams of hydrogen. Okay, so we'll need that. Okay, we'll also need the molar mass of ammonia here. Okay, so let's go ahead and write that down as well, which is going to give us 1 mole of ammonia. Okay, and then that'll be 17 grams of ammonia. And so there it is. We have then moles and grams. There's grams of ammonia there. There's grams of hydrogen there. Okay, now we have the moles here, and we're going to have to pick one of these conversion factors up here as our third conversion factor. And I hope you see then the only one that relates, that has both hydrogen and ammonia is the middle one here. So we'll write that down. So we have 3 moles of hydrogen, and that's from the balanced equation, every 2 moles of ammonia. Okay. All right. So hopefully you see then so we're going to use 3 conversion factors here, folks, to get this done. So hopefully you see then the very first conversion factor we're going to use is this one here, because we need to cancel out grams of hydrogen. So let's go ahead and plug it in as 1 mole of hydrogen, and make sure you understand why we do this. over 2 grams of hydrogen. We're going to plug it in as 1/2, which we're going to divide, means we're going to divide by the molar mass. Why? Because it allows us to cancel that out. At this point, then we have moles of hydrogen. We can't reuse this, so don't reuse this. Remember, after you use a conversion factor, you can't use it again. So the only other conversion factor that has moles of hydrogen is the third one here. So we're going to plug that in. Okay, we're going to use that next because we need to eliminate and cancel that out. If you notice here, we will plug it in as 2 moles of ammonia over 3 moles of hydrogen. Okay, and that allows us to cancel that out. But at this point, we're not done because this is moles of ammonia. We've got grams of ammonia. Okay, so we've used that conversion factor, and so don't reuse that. So we're left with one last conversion factor that we need to do, use. And so here then, if we plug it in as 17 grams of ammonia over 1 mole of ammonia, okay, we then cancel out this unit here. And so as you notice, as you go through this, and as we end up with here, we have then grams of ammonia on one side, grams of ammonia on the other side. We are done with our conversion. Okay. So at this point then, we just carry through the numbers, make sure you plug all these numbers correctly into your calculator. And if you do, you should finally get your answer then as being 30.6 grams of ammonia. Okay. Folks, that's stoichiometry. Stoichiometry is basically setting up the correct conversion factors, okay, and using enough of these conversion factors to get our conversion done here. But folks, again, it's still a conversion, which means then there are 3 questions you need to ask yourself. What do you start out with? What do you want to solve for? And then go ahead and then identify the conversion factors that you need. The only difference with stoichiometry now is you need more conversion factors in order to get this conversion done, okay? And so with that said, then I reached the 25-minute mark there. And so what I would like you to do then, and I'm sorry, one last thing, just be mindful of significant figures. When you do these problems, you're always check for significant figures are correct at the end. Okay, so always be mindful of significant figures, Jim. And so what I would like you to do then is actually, I would like you to work this problem out. This is the problem that we'll finish up with, and work that out on your paper and submit it. And what I'll do is tomorrow, we'll start with this problem here. So to finish out here, I won't assign, there will not be any problems from your textbook today. This will be the problem that you will include on your paper. And this is the final problem that you'll do, and then you'll turn it into me. Okay, so no problems from the book today. Please work out number 9 here in your problem set. And then what I'll do is I will start with this this particular problem tomorrow. Okay. I hope you'll be able to get the video watched and done today. And like I said, if you have any questions, just email me or make sure you comment on Google Classroom. And then, or like I said, come by tomorrow, I'm sorry, this afternoon, and ask your questions through our Zoom meeting. Okay. All right, folks, I will see you either this afternoon or I'll see you tomorrow.